Hello and welcome everyone. I'm Dinshaw Balsara, and this is joint work that I've done with my postdoc Deepak Boria, as well as Professors Chivang Shu from Brown University and Professor Harish Kumar from IIT Delhi. So it essentially concerns the following fact that finite difference we know for systems, hyperbolic systems with conservative products has been around for conservative hyperbolic systems has been around for a while, but we don't have any equivalent finite difference we know formulation for hyperbolic systems with non-conservative products, and especially with stiff source terms. Now, it actually turns out that in more recent years, there has been a great drive towards tackling hyperbolic PDEs with non-conservative products, and those PDEs oftentimes tend to also have stiff source terms, and so we're essentially interested in focusing finite difference we know schemes to have those capabilities. So let's go ahead and proceed. Okay, so the plan of the talk is as follows. We will first discuss why we want to take an interest in finite difference schemes, and we will also recap finite difference we know schemes for hyperbolic systems that are exclusively in conservative form, so that we can actually go ahead and reset our thinking. Then we will actually go ahead and explore what will and will not work for hyperbolic PDE systems with non-conservative products. Then I will actually tell you about a special Riemann solver, the simplest of its kind, which will actually tackle non-conservative products quite well. And then I will give you the form of the final finite difference we know scheme for hyperbolic PDE systems with non-conservative products. We will then mention accuracy analysis for those hyperbolic PDEs in conservative and non-conservative form. We will then talk about 1D Riemann problems and also focus a little bit on well balancing. Then we'll talk about multidimensional problems, test problems with stiff source terms, and then we'll go ahead and end with conclusions. So let's go ahead and think about it. So suppose you're given a simple conservation law, namely the time rate of change of u is actually proportional to the gradient of f. There are two ways you could go about it. You could actually go ahead and choose a finite difference approximation, or you could go ahead and choose a finite volume approximation. What is the difference between them? The bottom line is that a finite difference approximation is defined on a mesh so that it's actually defined at the zone centers of that mesh, which is what is shown to you out here. So ui minus 1, ui plus 1, etc. on the top mesh are defined at exactly point values at the zone centers of that mesh. And then we want essentially the fluxes at the zone boundaries. And we can get those fluxes at the zone boundaries if we go ahead and directly reconstruct on the point values of the fluxes at these particular zone centers. And that is what gives us a finite difference approximation. As you increase the order of accuracy of the fluxes, you get the increase in the order of accuracy of the update. Of course, I'm showing you a first order update, but you can couple this with the Runge-Kutta time stepping in order to get higher order accurate update. Now notice that the caret on top of the fluxes indicates that we're actually using point values that are obtained via some sort of reconstruction. Now, what is the other alternative? The other alternative is to actually take your conservation law and integrate it over space and time. Therefore, this U bar is actually a zone averaged or a volume average representation of u in the zone I, and you can actually have similar representations in the other zones. And in doing so, you actually go ahead and reconstruct u bar, or you reconstruct u itself so that you respect the zone averages and so on and so forth. And once you do that, you can actually go ahead and do a space-time averaging in order to obtain these fluxes. So the over bars in this formula out here, or in this formula out here, are meant to kind of indicate that these are the u bars are spatially averaged and the fluxes f bars are space-time averaged. So there are two different very different approaches to doing this, and let's go ahead and now view the strengths and weaknesses of these two approaches. So why would people choose finite difference schemes? It turns out that finite difference schemes are amongst the most well-cited schemes around, so they've clearly played an important role in science and engineering problems, and that comes about because for one dimension, finite difference and finite volume schemes are both equally fast. However, for multidimensional problems, the finite difference reconstruction is extremely simple and low cost, whereas the finite volume reconstruction, as you go to successively higher orders, involves many more multiple cross terms in the moments that you have to reconstruct, and that increases the cost of one single stage of your finite volume approximation relative to the finite difference approximation. So we all like lower cost, therefore we prefer finite difference approximations for certain applications where we can benefit from them. This advantage also extends to time stepping. So this advantage also extends to time stepping in the sense that if you're doing any sort of Runge-Kutta update, then at each stage in your Runge-Kutta update, you will have to reconstruct all these extra cross terms, and that will actually even add further to the cost. This penalty does not extend to finite difference approximations, only to finite volume approximations. If you're using any sort of Lax-Weintraub type scheme or Ader type scheme, you will actually have to evolve those extra cross terms, which additionally adds to the cost. So there's a big efficiency advantage for finite difference approximations. The finite difference approximations also have a gigantic advantage because their primal variables are point values at the zone centers. And as a result, if you have any sort of stiff source terms in your problem, then that update can be a pointwise update, which makes it very efficient. And that is very efficient compared to finite volume schemes where all across the zone you might have to solve for those stiff source terms. So you have many more matrix inversions if you have stiff source terms in a finite volume approximation than if you're using a finite difference approximation to solve the problem. Now there's no such thing as a free lunch, which basically means that there are also some drawbacks associated with finite difference schemes. Namely, if you have some sort of gentle enough mapped grids, you can actually accommodate finite difference schemes to them quite easily. However, if you have a truly unstructured mesh or something like that, or a very complicated mesh, you will definitely need finite volume schemes. If you have any geometrical involution constraints like a div preserving or a curl preserving involution, then you will definitely need finite volume schemes because they have certain algorithmic flexibility. In a finite difference scheme, you only have point values, so there's not that much algorithmic flexibility. This algorithmic flexibility also extends to adaptive mesh refinement because there too, the fact that you're defining things in a finite volume sense can actually help you quite a bit. So with that, let's go ahead and do a quick review of the pre-existing finite difference WENO schemes for conservative hyperbolic partial differential equation systems. And it's important to realize that a finite difference approximation is very Spartan in the sense that all you have is the point values, and from those point values, you have to go ahead and make up your entire scheme. So what would you have if you had a finite difference approximation and you had a certain flux? Then you would actually resort to an LLF, a local Lax-Friedrichs type of flux splitting. And how does that work? It basically works on first getting the spectral radius of your Jacobian matrix. Operationally, this is nothing but analyzing the Jacobian matrix of the flux, obtaining the eigenvalues and obtaining the maximum value of those eigenvalues, and using an S value that is kind of comparable to the spectral radius. So you start with a flux and you write it as half of F plus SU and half of F minus SU. And notice that you could add these back up and get F. So there's no difference. But the important thing is that half of F plus SU is a flux for which you will only have positive eigenvalues. Half of F minus SU is a flux for which you will only have negative eigenvalues. So we kind of identify them as F plus and F minus respectively. And notice that F plus captures the propagation of only right-going waves, F minus captures the propagation of only left-going waves. And with this, we can actually now go ahead and specify the flux at the zone boundary I plus a half. We can actually go ahead and say that what if we want F plus? We will get that from the zone UI, which actually contributes right-going waves. And so at this zone boundary, we will obtain F minus of I plus a half. Likewise, we can actually say, how do we get F plus at I plus a half, at zone boundary I plus a half? And the answer is that the zone I plus 1 will contribute how do we get F minus at zone boundary I plus a half? And then the answer is that the upwinded zone relative to that boundary is U I plus 1, and it will actually contribute F minus at the zone boundary I plus a half. So with that, we can actually go ahead and split the flux into a right-going flux from zone I and a left-going flux from zone I plus 1 at the zone boundary I plus a half that is of interest. This is also shown with the stencil operations out here. So you have right-going waves from the right-going flux, and you have left-going waves from the left-going flux. So focus on the purple zone boundaries, because that is where we want to kind of illustrate the construction of the flux. Now, how do we go to a higher order extension? And the answer is that we must include the upwinded zone for that particular flux. So for F plus, we must cover zone I, and for F minus, we must cover zone I plus 1. But with that caveat, we can basically go ahead and use any consistent version of point values or any consistent set of point values to build a consistent value for F plus, and we can use any consistent set of values of F minus as long as they cover zone I plus 1 to obtain F minus. So with that, we can actually imagine doing a higher order extension, and that's shown in this figure out here. So essentially, the zone I is going to contribute right-going F pluses to this zone boundary I plus a half. So you're going to get your F pluses from here at the zone boundary I plus a half. And you're going to do that by basically evaluating F plus at zone I minus 1 and zone I plus 1, and using these two stencils, these two red stencils shown out here, you can actually go ahead and make a nonlinear hybridization with higher order accuracy for F plus at zone boundary I plus a half. Similarly, you can actually go ahead and say which is the zone that contributes upwindedly to the F minus, and that's the zone I plus 1. And so as long as you include zone I plus 1, you can use these blue colored stencils, namely these two guys, to actually help you evaluate the flux F minus at I plus a half. So with this, you can obtain higher order extensions. There's a slight subtlety as to why this works for finite difference, and that's explained in this paper, this review paper out here. So I'd urge you to kind of go ahead and look into that to understand why the flux vector splitting works at higher orders. And this actually goes ahead and opens the door to obtaining higher order accurate representations of finite difference. We know for conservative PDE systems, conservative hyperbolic PDE systems, where basically we want a very high order accurate representation of F plus at the zone boundary I plus a half and F minus at the same zone boundary I plus a half. And this is actually illustrated to you impressionistically, at least, by this figure out here. So imagine if you want that we want to focus again at zone boundary I plus a half, we can actually go ahead and choose this big stencil, and for all the zones that are covered by this big stencil, we can actually evaluate F plus from those zones. If that stencil is actually smooth, we can take the solution, we can take the smooth solution of that guy to obtain F plus at zone boundary I plus a half. But if not, we can actually resort to these smaller third order stencils, and you can actually go ahead and drill down in the order of accuracy as much as you wish to obtain f plus at I plus a half, which is properly nonlinearly hybridized. How do we obtain f minus at I plus a half? The answer is that you go ahead and use this big stencil to try and first obtain a fifth order accurate representation of f minus of I plus a half. And if that fails, if you have a non-smooth solution on that big stencil, then you actually go ahead and drill down further, use these smaller, perhaps third order accurate stencils to actually nonlinearly hybridize between them and obtain f minus at I plus a half. You put those two fluxes together and you have a very high order accurate representation of the flux at the zone boundary I plus a half, and you put that together in your finite difference approximation and you get a good scheme. So there are many smaller observations that we can make. One is that we realize that you have actually two reconstruction steps going on, one for the evaluation of f plus at each zone boundary and one for the evaluation of f minus at each zone boundary. We would like, if we could, we would like to have only one reconstruction step per flux evaluation, because you realize that for finite difference we know the reconstruction usually has to be in characteristic space if you want nice solutions, and that characteristic projection and construction of eigenweights and then reprojection of those eigenweights onto the right eigenvectors is usually a rather expensive step. Okay? Now notice another important deficiency, which is to say that the method cannot hold stationary discontinuities. We also have a problem with well balancing, and the Riemann solver that we use, namely the LLF Riemann solver, does not have a good supersonic limit. Now, a major drawback, those were minor drawbacks or minor issues, minor quibbles that one can have, but a major drawback with this finite WENO formulation is that, as described, it is not suited for problems involving, for PDEs, for hyperbolic PDEs that involve non-conservative products. And so we would actually like to have a finite difference WENO formulation that works with non-conservative products and also stiff source terms, because that seems to be the way, where the invention of new PDE systems is headed. Namely, there are a lot of new PDE systems that are being invented for solving various important science and engineering problems, where you actually need absolutely to take care of non-conservative products and also stiff source terms. So the French have a very nice saying that it's important to step back a little bit before you can make an advance. So let's go ahead and step back a little bit and think about what our options are. So let's go ahead and now focus on hyperbolic partial differential equation systems that have non-conservative products. So a typical hyperbolic system that has non-conservative products looks like this equation out here, where you can actually see that du by dt is proportional to the gradient of the flux just as before, but we have an additional term which simply cannot be factorized into a gradient of something, which is structured so that you have this matrix C times d by dx of u. Now, of course, if you cast this in characteristic form, which is this form out here, then you realize that A is nothing but the Jacobian of your flux plus the matrix of non-conservative products. But the problem is that you cannot write this Jacobian as a gradient, as d by du of something else, which is why these products are called non-conservative products in the first place. So what we want to do is we want to find a representative or sample PDE system for which it can transition, which can actually transition seamlessly to a flux form and also transform seamlessly to a non-conservative product, so that we can actually go ahead and use that system as a mental crutch with which to kind of inform our thinking. And that's what we're going to do for the next few transparencies. So what we're going to see in the next few transparencies is just an effort to produce such a mental crutch. After we produce such a mental crutch, we will actually eventually give it up, but it's important to have such a mental crutch. So what is such a PDE system? We can start with the conservation law and imagine a flux that is given by a constant matrix A times the vector of conservative variables. As long as A is a constant, this PDE system can as well be written in non-conservative form as follows on the right. So you can actually, as long as you have F is equal to AU with A a constant, you can transition from a flux form to a form that seems like a non-conservative product. So let's go ahead and work with that situation for a while. Just get some insights associated with that. Okay, that's all we're doing. So we can now go ahead and use our same basic idea, namely we want to obtain a flux vector splitting into an F plus and an F minus at each zone boundary, and therefore we can go ahead and write F at the zone boundary I plus a half as half of F plus SU at zone I and half of F minus SU, all evaluated at zone I plus 1. Now, the only thing that we're going to do is we're going to assert that F is equal to AU. So wherever we have Fi, we're going to replace it with A times UI. So we get an F plus from here. And wherever we have Fi plus 1, we're going to replace it with A UI plus 1. So we're going to get our F minus from here. And that actually tells us that the flux can be written as A plus of UI, the upwinded flux that is going to the right, and A minus of UI plus 1, which is the upwinded flux that is going to the left. And so we're in good shape now, because we can actually realize that if we want the flux at this zone boundary at I plus a half, we can obtain A plus of UI from the left and A minus of UI plus 1 from the right. And as long as you do that, we'll have at least a properly upwinded first order flux, and it kind of gives us the insight that these matrices A plus and A minus are going to play some important role in our dialogue. Okay, so with that we can actually go ahead very quickly write in terms of A plus and A minus a flux at each zone boundary, which is this guy, and this guy at zone boundaries I and I plus half and I minus half. And therefore we can put together a basically first order numerical scheme like this one out here. This figure is exactly the one that we discussed before, and this is actually just your Lax-Friedrich scheme, so nothing new out there. But now we can actually go ahead and say that how would we start with this Lax-Friedrich scheme and hybridize it or update it to higher order accuracy? How do we go ahead and do exactly that? And the answer then is that we can actually go ahead and say that we have a basic idea that A plus takes contributions from the left of the zone boundaries and A minus takes contributions from the right of the zone boundaries. So this first order scheme is then upgraded at higher order of accuracy to this scheme on the right. So that this scheme on the right, as long as your reconstruction of U minus and U plus at the zone boundaries is higher order accurate, you will actually get a higher order scheme. So this is a good thing, and we now go ahead and do our reconstruction in the zone I to obtain U minus at I plus a half and U plus at I minus a half, and we again do our reconstruction in zone I plus 1 in order to obtain U plus at I plus a half and U minus at I plus 3 over 2. So with that, and we can continue this process for all zones, and therefore we can actually obtain a scheme that is higher order accurate. At least for constant A, this scheme will actually be fine. Okay. So when A is a constant matrix, this scheme is higher order and even conservative, even in multi-dimensions. And when A is a constant matrix, the scheme is effectively the LLF scheme from Shu and Osher. So we have our moorings in the sense that we have now a seemingly non-conservative scheme. Of course, it is conservative because A is a constant matrix, but we have a seemingly non-conservative scheme which is actually cast so that it is effectively equivalent to the LLF scheme from Shu and Osher 1988. So we have our moorings in place, and now we're going to build on. Now, what if your hyperbolic system has non-conservative products, but it is a nonlinear hyperbolic system? Okay, then it has this general form, which basically means that you can write it as a characteristic matrix like so, with the characteristic matrix being defined as a Jacobian of the flux plus the matrix of non-conservative products. And now, if you are desperate, you can actually go ahead and define A plus associated with zone I, and you can define A minus associated with the zone I. And therefore, you can upgrade the scheme that we had before, which was that scheme that we saw in the previous transparency, into this scheme out here. So the only difference is that we've maintained everything exactly as it was in the previous transparency, all the higher order accuracy and everything. The only difference is that A plus and A minus in this equation are not constant matrices. They're basically matrices that can change with every zone. Okay? So this scheme might in fact retain higher order accuracy because it is in fact truly consistent with the scheme from the LLF scheme from Shu and Osher 1988. But the problem is that it's not in conservation form even when C tends to 0. This method is actually not good at preserving stationary contact discontinuities because we've done nothing to improve the situation associated with stationary contact discontinuities, and the prior scheme, the finite difference WENO scheme from Shu and Osher 1988, was in fact not able to preserve stationary discontinuities. But it does have one advantage, and that one advantage has to do with the fact that you can get by with only one reconstruction per zone. And so this is a very good advantage, and we would like to retain that as advantage as we move forward. But we realize that we've gone ahead and had a nice discussion, but we've reached essentially a dead end, and let's go ahead and find a way out of this dead end. So the way out of this dead end comes by essentially starting to think about simple Riemann solvers that have some nice products, that have some nice attributes, and then building on them. So we would like to build on the HLL Riemann solver. Why? Because it's the simplest Riemann solver that indeed has a supersonic limit. So imagine, if you like, that we have a solution of a Riemann problem. This is showing you the solution of the density variable from the Sod-Shock problem. And if you can go ahead and realize or recall that a Riemann problem is always a self-similar solution of a hyperbolic problem, you basically realize that its space-time diagram, namely the diagram in space and time of this hyperbolic problem, should consist of a left-going shock or a left-going rarefaction fan, a right-going shock or a right-going rarefaction fan, and a contact discontinuity. So there's a lot of substructure within this Riemann fan, and notice that this Riemann fan evolves self-similarly because it's evolving along straight lines in space and time. The whole point of the HLL Riemann solver is to retain these same extremal speeds, SL and SR, but to actually go ahead and replace the internal structure of the Riemann fan with something extremely simple, namely a constant U star and a constant F star within the Riemann fan. Once you have that, you can actually go ahead and, as long as SL and SR are chosen judiciously, you will have entropy enforcement in your Riemann solver. So typically we choose SL and SR to be identical to the SL and SR that you might have obtained from an exact Riemann solver, or your best approximation for an exact Riemann solver, which could be a linearized Riemann solver, for example. So with those preliminaries, we're now ready to go and do business. And what I would urge you to do is realize that we're trying to understand the transition from the HLL Riemann solver for conservation laws to an HLL Riemann solver with non-conservative products. So I'll always have a red arrow in the middle. On the left, I will show you in black what it looks like for a conservation law, and in the right of that red arrow, I will show you in maroon color what things look like for a system that has non-conservative products. So let's go ahead and do exactly that. Okay? So imagine, if you like, that we have a conservation law out here. For this conservation law, we can say that, look, we have a jump at this left going discontinuity SL, and therefore we'll go ahead and realize that because the gradient of the flux is in a perfect differential form, we can actually write the jump in the fluxes. We can write a weak solution for the shock jump. We can say that the jump in the fluxes is equal to SL times the jump in the states. Okay, that's at the left boundary of the Riemann fan. At the right boundary of the Riemann fan, we have waves propagating with a speed SR, and so we can say that the jump in the fluxes is equal to SR times the jump in the states, and that gives us two equations, 1 and 2, in two unknowns, namely F star and U star. So we have two equations and two unknowns. That's your elementary algebra type problem, and you can solve for U star as a function of the left and right states and the left and right fluxes. So easy peasy, that's your quickest derivation of an HLL type Riemann solver. Now let's go ahead and see how things change when we deal with non-conservative, a system with non-conservative products. Okay, so some things change a little bit. Now notice that the non-conservative products cannot be written as a perfect derivative of something, and so we will have essentially across this left-going boundary of the Riemann fan, we will have a shock jump condition which involves the jump in the fluxes plus the integration across this boundary of the non-conservative products, and that in turn is equal to SL times the jump in the states. Likewise, at the right boundary of our Riemann fan, which is this guy, we will have a jump in the fluxes plus some representation of the non-conservative products and how they change across this jump is equal to SR times the jump in the states. And now again we have two equations in two unknowns. The one unknown that we can quickly eliminate is F star, and so we go ahead and add these two equations together and we get this equation for the update of U star. Notice that this equation is nonlinear in the sense that U star appears even on the right hand side, so it will have to be iterated to convergence. Okay. Fortunately, the construction of the C-twiddle matrices is very easy, and especially for most typical hyperbolic systems for which we're designing our scheme, we would actually be able to construct the C-twiddle matrices quite easily because they have a majority of zeros and only a few non-conservative terms. Therefore, we can very quickly obtain U star as a matter of carrying out a fixed point iteration with a few iterates. And once we have U star, we can actually get pretty much everything associated with this Riemann solver. So we have a good situation, and now let's go ahead and see what insights we can get. So if we take the jump at the left boundary of our Riemann fan, we can actually massage the equation a little bit to get F star in terms of FL plus some additional contribution. So we'll write this as FL plus a left-going fluctuation D minus arising from the HLL Riemann solver. Okay, so we know the form of D minus HLL because it's essentially just this guy out here. Likewise, we can take the jump across the right boundary of our Riemann fan and massage it again so as to get F star in terms of FR minus some additional contribution, and we can write it as FR minus the right-going fluctuations emerging from our Riemann fan, and we know how to pick out the form of these right-going fluctuations. There's a little more complexity. If you're dealing with a general case, you might have to do a little bit of integration, but even so, the answer comes out to be the same, and you get your left-going fluctuation from the Riemann fan and your right-going fluctuation from the Riemann fan. These are basically the wave contributions emanating from the Riemann fan that are going to the left and going to the right of this central point associated with the Riemann fan. Notice that once we have U star, we basically have everything. The flux evaluation is just a nicety. This Riemann solver, as given so far, will not be able to hold or retain stationary contact discontinuities on the mesh, so we will need to pay additional attention to well balancing if we were to use it or improve this Riemann solver, and this is essentially a diffusion issue. However, note that we have won something because this Riemann solver does have a well-defined supersonic case. And this Riemann solver is very diffusive simply because we washed out all the substructure in the Riemann fan. So now we want to go ahead and put back some of that substructure so as to remove some of the diffusion. So we call this an anti-diffusive flux. So let's go ahead and see how that works in the next transparent. And we realize that if we want to remove the substructure in the Riemann fan, we still have to retain the idea that a Riemann problem is in fact a self-similar solution of a hyperbolic problem, and therefore we have to the substructure that we can put in depends only on the similarity variable, which is the ratio of x over t. So notice that in this figure we would like to put in substructure, but along each of these blue colored rays that you see, the solution will be a constant. Now, what is the simplest form of substructure that we can put in? The answer is that we can put in a linear profile. So we can put in substructure so that C at SL is just minus a half. That's what you would identify from this function. And C at SR, this function evaluated for C is equal to SR, gives you plus a half. So this function that I've just identified out here, evaluated at C is equal to SL, would give you minus a half. This function evaluated at C is equal to SR would give you plus a half. And that actually allows us to put in a linearly varying profile inside the Riemann fan. How much should this Riemann fan, how much should this change be proportional to? The answer is we can take a cue from the row-type Riemann solver and realize that we have an eigenweight out here, which is just the left eigenvector associated with a particular wave family, multiplied by the corresponding right eigenvector. So left eigenvector dot producted with UR minus UL gives you an eigenweight, and that eigenweight when multiplied with a right eigenvector gives you a contribution to this thing. And so we want a further contribution from a particular wave, namely the pth wave, that is proportional to this. And then there's this one extra piece which actually modulates the amount of anti-diffusive flux that we can put in. It's basically carefully adjusted so that you put in not any more anti-diffusive flux than you should, because if you overdo it, then of course you will actually wind up with an unstable numerical scheme. So it gives you the maximum amount of anti-diffusive flux that you can put in while remaining safe. So it keeps you safe and it allows you to minimize the diffusion. So with that, that secret sauce is carefully calibrated and it's documented in papers which we can point you to. Okay, so we have a left-going HLL fluctuation and a right-going HLL fluctuation. And to that, we just subtract off this anti-diffusive flux on one side and add the same amount of anti-diffusive flux on the other side, and that gives us fluctuations with a reduced amount of dissipation in them, and that gives us improved fluctuations called the D minus HLLI and D plus HLLI. So this I stands for intermediate states or intermediate waves that you can put into the Riemann fan, and you can put in just the important self-steepening or anti-diffusion that you want for particular wave families that you're interested in. You don't have to put in anti-diffusion for all the possible wave families, but you have a closed form formula which you can evaluate and go ahead and make progress with. Notice that this L times UR minus UL is just an eigenweight out here. The delta is the modulating factor that you have to just retain stability. This is the matrix of right eigenvectors, and this is just a coefficient that you have, then an additional coefficient that sits in the front. Okay, so we put in equal amounts of anti-diffusive flux subtracted from one guy and added to the other guy, which actually allows us to reduce the diffusion in our fluctuations, and that allows us to make progress. So with that, we're now ready to actually specify the scheme. So notice that A minus is evaluated at zone UI, and we go ahead and carry out a higher order reconstruction of the solution vector itself. In other words, we choose a large fifth order stencil if you want a fifth order scheme, and if this fifth order stencil has some roughness on it, then we can nonlinearly hybridize it so that we can choose any one of these three left biased, centrally biased, or right biased third order stencils to obtain a lower order representation of the flux or lower order representation of the reconstruction, and that allows us within each zone to obtain U minus at the right boundary of the zone and U plus at the left boundary of that zone. Okay, so with that we can actually go ahead and construct this term out here, which actually represents the time rate of change within a zone without accounting for the fluctuations, that the left going fluctuations that are coming from the I plus a half boundary and the right going fluctuations that are coming from the I minus a half boundary. So we can account for those by putting in this additional term. So we have D minus HLLI from the I plus a half boundary, and we have D plus HLLI from the I minus a half boundary, and that accounts for the contributions coming from the Riemann fan. So we have a central contribution, which is this guy out here, and a contribution from the Riemann fans at each of the zone boundaries, which is this other guy out here. Okay, so that is essentially our numerical method. Now, how does this numerical method actually work in practice? I give it to you in one single transparency, and it's very simple. The answer is that you focus again on the purple zone, and in the zone UI, you obtain U minus of I plus a half and U plus of I minus a half by doing a reconstruction step, and you do such a reconstruction step for all the zones in this problem. And once you do that, you will have left and right states at each zone boundary. For example, we're considering I plus a half. Once you get the left and right states for each zone boundary, you can obtain the resolved state U star I plus a half for that particular zone boundary of interest, and we obtain this for all the zone boundaries of interest. Once you have U star and the left and the right states, you can actually obtain the left going fluctuations and the right going fluctuations at all the zone boundaries that you're interested in, and that allows you to put together this part of your right hand side. This is the time rate of change from the fluctuations that are emanating from the Riemann fans. You can also obtain A of UI and multiply this with the update from the internal values within the zone itself. Notice that we have U minus of I plus a half, which is this guy, and we have U plus of I minus a half, which is this guy out here. Okay, so I'll erase much of the very dominant underlining in this transparency, and this allows you to see the update strategy. The update strategy is extremely simple, and you couple this time rate of change with a Runge-Kutta stage, a multi-stage Runge-Kutta updating, and you obtain a higher order Runge-Kutta in time update strategy, and you're done. Okay? How the Riemann solver? This page actually allows you to highlight many aspects of the HLLI Riemann solver. The I stands for the ability to introduce intermediate waves. So this convergence to U star can be carried out by fixed point iteration. It actually converges very quickly, especially for PDE systems of interest, where you have just some smattering of non-conservative products. Notice that we're not being very ambitious. You're not going to be able to recast a PDE in non-conservative terms and work with the non-conservative variables, but at least for PDEs where you have a conservation law and some non-conservative products, this will allow you to converge very easily to U star. Once you have that, notice that you have a well-defined supersonic limit. So if all the waves are moving to the right, then you can use these fluctuations. If all the waves are moving to the left, you can use these fluctuations, and if you're subsonic, then you can use these fluctuations out here. This gives you the HLL fluctuations from the zone boundaries, and then you can actually go ahead and evaluate your antidiffusive flux and add the antidiffusive flux to the D minus and subtract the antidiffusive flux from the D plus, depending on what sign you want for the antidiffusive flux. And this actually allows you to minimize the diffusion. So we have a Riemann solver that has a proper supersonic limit and also allows us to minimize the diffusion, which will help with well balancing. So now let's go ahead and proceed. Okay. What is the multidimensional extension? We told you that multidimensionally finite difference WENO schemes have a gigantic advantage. So if you have a two-dimensional hyperbolic PDE system with non-conservative products in the x direction as well as in the y direction, then this scheme is especially beneficial. Why? Because you apply the same strategy to the x direction and the same strategy to the y direction. In fact, in our applications codes, we don't even write a different strategy from the x direction and the y direction. We just specify that the direction is 1 or the direction is 2 or the direction is 3 for the x, y, and z directions, and we use the same subroutine, so it's very easy to code up. Okay, because this is a finite difference scheme, the multidimensional extension is very easy, and you just do it dimension by dimension. Now, notice that you only require one WENO reconstruction step, which is a gigantic advantage over the classical finite difference WENO, which required 2 reconstruction steps. And this is because you're doing it in characteristic variables, so those reconstruction steps are rather expensive, and by reducing the number of reconstruction steps, we've actually gone ahead and reduced the cost of the numerical method. It can handle PDEs in conservation form just fine, just perfect, but it has the additional advantage that it can actually handle PDEs, hyperbolic PDEs that have non-conservative products. So that is a good thing. Okay. We can also include antidiffusive fluxes, which ensures that we can hold stationary discontinuities on the mesh. This will actually help us greatly with well balancing. Also note that our Riemann solver has a well-defined supersonic limit, and that is a good thing because we can now, it actually helps us a little bit. And notice that because our antidiffusive terms are self-adjusting, even if we use the LLF variant of the HLL Riemann solver, we can actually go ahead and put in heftier amounts of antidiffusion and therefore hold stationary discontinuities even with an LLF type formulation. That is one of the better aspects of this. The only thing that you might need to do is you might, for different PDE systems, design a different flattener function psi so that you don't overdo your antidiffusive fluxes in situations where you have strong shocks, etc. So this might be something that you have to custom design a switch. You might need to custom design a switch for different PDE systems. With this, we're ready to move forward. Now, it is my job to essentially prove to you that this numerical scheme, which is a different formulation, is essentially identical to the classical finite difference WENO in its LLF form in the limit where linearizations are valid. Okay, if that is the case, then you will be able to do one-dimensional and multidimensional problems with sufficient order of accuracy that you'll be happy. So this is our actual new proposed scheme. This is the scheme that we got by just our little conceptual thinking that we had done in a prior section, 2 sections before, and we know that this scheme is essentially identical to the classical finite difference WENO LLF scheme in the limit where A is a constant matrix, or in the limit where A plus and A minus are constant matrices. We therefore want to show that we can start with this guy out here, and through a sequence of manipulations, at least in the limit where A is a constant, we can obtain this guy out here without a problem. So let's go ahead and see exactly how this works. Okay, so keep your eye focused on this second equation on this page. I'm going to just go ahead and transcribe it to the first equation on the next page. So this is just the previous equation that you've seen. And all I'm going to do is subtract and add the same additional term. Now I realize that this term that I've subtracted out here is exactly identical to the internal update term that in our new scheme. So I go ahead and club all the remaining parts of this equation into parts that will look like my fluctuations. So that's what I do. So I have my update from the internal terms, and here's my update from the fluctuation terms. Notice that I have explicit expressions for the fluctuation terms, at least in the limit where A is a constant matrix, and I'm using an LLF Riemann solver so that I put my extremal right going speed to be S and my extremal left going speed to be minus S, where S is your spectral radius. So with that, you can actually obtain, you can just go through the machinery of an LLF type Riemann solver. This is the HLL Riemann solver with these specific limits on the wave speeds. And so you can go through the machinery of that, and you can obtain an expression for D minus and an expression for D plus, which is these expressions out here. Now, it's very easy to show through a sequence of manipulations that this D minus expression that you got is identical to this expression out here, which is essentially this expression out here. And it's very easy to show that this expression that you got for D plus is identical to this expression out here, which is essentially this expression out here. And that allows us to see the connection between this manipulated equation and this final expression of the new scheme. In other words, we have our update terms from the inside of the zone itself, and we have our left-going fluctuations from the right zone boundary from the Riemann solver, and we have our right-going fluctuations from the left zone boundary from the Riemann solver at the left zone boundary. So with this, we're home free. We realize that the new proposed scheme in the limit where A is a constant matrix, or in the limit where A can be linearized, is essentially identical to the scheme at the top of this page, which we know to be identical to the classical finite difference we know in its HLL form. I'm sorry, I meant identical to the classical finite difference we know in its LLF form. Okay, so just to recap this rather dense mathematical page, we started with the premise, or we started with the understanding that the equation on the top is identical to the classical finite difference we know in its LLF form from Shu and Osher 1988. And we were able to show that at least in the limit of linearization, this scheme at the top, namely this guy out here, is identical to this scheme at the bottom, which is our newly proposed scheme. Of course, the newly proposed scheme has many more bells and whistles with which we can improve the quality of solution, but in doing so, we have ensured that the scheme on the bottom is also going to preserve order of accuracy, and especially in multi-dimensions. So that is a good demonstration, and with this demonstration, we're kind of ready for business. So now it's just a matter of my proving to you that we are able to maintain order of accuracy analysis, and we're able to produce schemes which meet their design order of accuracy. And we're going to do that for the Euler equations as a prototype of a system in conservation form. And we're also going to focus on compressible Baire-Nunziato multi-phase flow, which is a PDE system that has conservative fluxes as well as some non-conservative products. We're also going to focus on the two-layer shallow water equations, which is again a PDE system with fluxes and some non-conservative products, and we're also going to focus on multi-phase debris flow, which again has the same structure, namely flux terms plus some non-conservative products. And we're going to basically use the latter three PDE systems to exemplify the performance of the scheme on PDE systems that have non-conservative products. We're also going to do some problems with stiff source terms. So for problems that don't have stiff source terms, we're going to use the SSPRK3 and SSPRK4 schemes, which are very popular. And for problems that have stiff source terms, we're going to use a third order accurate IMEC scheme from Peresci and Russo, which is also SSP in its behavior. So let's go ahead and focus on the two-dimensional hydrodynamical vortex problem. So this is a vortex that is set up on a square mesh and allowed to kind of periodically go around the mesh once or twice or as many times as you wish, but we only try once. And we now see that our third order scheme meets the third order accuracy, our fifth order scheme meets fifth order accuracy, and our seventh order scheme meets its seventh order design accuracy. So those are good. We can also focus on our first example of a PDE system with non-conservative products. You can see those non-conservative products out here. Okay, and this is our compressible Bayer-Nunziato multi-phase flow. It represents the flow of a solid phase in addition to a gas phase. So the solid phase is shown by the subscript 1, the gas phase is shown by subscript 2, and we have an interfacial velocity between the two phases, which is shown out here. And basically, this is a multi-phase flow problem. The phases have to add up to 1, and that's governed by this equation out here. So with this, we can actually show, or we can set up a two-dimensional vortex problem and show that for this multidimensional flow problem involving the Bayer-Nunziato equations, again, our third order scheme is third order accurate, our fifth order scheme is fifth order accurate, our seventh order scheme is seventh order accurate, and things work out. Then actually go ahead and focus on our shallow water equations. So imagine, if you like, that you have a lake out here and you have one layer of fluid and you have another layer of fluid on the lake. So you can actually imagine that the bathymetry is the height of this bottom of the lake relative to some reference point. H1 represents the height of the first fluid, so this is H1. I'm sorry, this H1 is the height of the second layer, so this is H1, and this is H2, the height of the bottom layer of the fluid, and this is B, the bathymetry. And so I should have drawn H1 and H2 differently, but anyway, you get the picture and you can actually look up the equations. So I'm sorry if I didn't explain that perfectly, but it basically tells you that the bottom of the lake can have variable bathymetry, and the variable bathymetry and the other terms actually conspire to produce these non-conservative products out here, which is the point of interest for this PDE system. Likewise, so you can actually see that our schemes at third, fifth, and seventh order meet their design accuracies. And you can see that we have the shallow water, the multi-phase debris flow problem, and again we have a fluid layer and a solid layer, and we can actually go ahead and see the structure of the non-conservative products out here. And again, this is a PDE system with fluxes and non-conservative products, and you can actually see that another two-dimensional vortex flow problem that we've been able to use has third order, fifth order, and seventh order accuracies as designed. We can now go ahead and do one-dimensional Riemann problems to make sure that things are working. And this is the interacting blast wave problem from Woodward and Colella, where you have two very strong blast waves coming in from both sides of this boundary and interacting in the middle, setting up this interesting density structure. And you can see that our third, fifth, and seventh order schemes are actually meeting are matching with the converged solutions. This is the Abgral test problem for compressible Bayer-Nunziato multiphase flow, where we have a variation in the phase, that's this shown by this one, and you can see that the velocities in the two phases, U1 and U2, are constant, and the pressures in the two phases are maintained constant. So you should be able to advect a phase change while retaining constancy of velocities and pressures. So that's shown to you in the top panel, and the variation in the phase itself is shown to you in the bottom panel. Again, we have third order, fifth order, and seventh order schemes out here in these three different columns. So things are working well. We can also go ahead and do a raft of Riemann problems associated with Bayer-Nunziato flow, which is shown to you out here. So there's 1, 2, and 3 Riemann problems shown in the left column, the middle column, and the right column. And we have another set of 3 Riemann problems which are shown in the left, middle, and right columns for the fourth, fifth, and sixth Riemann problems. And again, things seem to converge to the right points. We can even do shallow water equations, where you have out here a stationary discontinuity formed by linearly degenerate characteristic fields, and you can actually see that over hundreds of time steps this discontinuity is identically preserved very nicely on the mesh without any introduction of numerical dissipation. So the ability to capture stationary discontinuities is good for our numerical method. We can actually go ahead and see two different Riemann problems, one on the left and one on the right, associated with our two-layer shallow water equations. And we can actually go ahead and see the well-balancing property. So this actually shows the bathymetry, the variation in the bathymetry as a function of position. I'll remove the marking so that you can see that variation in the bathymetry, and a small disturbance is put in the center out here, like so, for example, approximately. You can check the details in the paper, but the variation of the two layers of fluid as a function of time at a later time are shown to you out here. The left panel shows you what happens when you have a large perturbation in the problem, and the right panel shows you what happens when you have a very small perturbation in the problem. So you can actually see that these variations out here are extremely tiny, showing us that the variations in the variables eta and eta2 that need to actually tend to 0 or tend to constant numbers are actually being preserved. You don't have any numerically generated storms in this sort of problem. With this, we can actually go ahead and do multi-phase debris flow. Again, we have a stationary discontinuity involving multiple linearly degenerate characteristic fields, and you can see that those discontinuities are properly preserved in all the flow variables of interest. So that is a good thing. We also have the ability to do multiple Riemann problems, and we also have the ability to obtain well-balanced solutions to various situations. So the left, middle, and right panels show the operation of third, fifth, and seventh order numerical methods. We can also do multidimensional test problems. So we have the forward-facing step from Euler flow out here, very classical test problem, again drawn from Woodward and Colella, which actually shows the vortex sheet roll-up that is expected from a low dissipation numerical method. So that is a good thing. Likewise, we have the double Mach reflection problem, and again you can see the zoomed in picture of the curled up Mach stem. So it shows that our numerical method retains its low dissipation properties. This is a problem from compressible Bayer-Nunziato multiphase flow, where initially a shock is initialized somewhere out here, and there's a dense blob of solid density, and as the shock moves in on this blob of solid density, things actually go ahead and discombobulate, so that at late time you can see that the shock has completely overrun the solid density, and you can see the solid in its distorted phase out here, in a distorted state out here, as it has been blown up by the shock problem, that shock wave that propagated right through it. And you can see that this matches the expected and published results. These are problems involving shock interaction with a vortex, so the shock is visible from these boundaries out here in the velocity pictures. So on the left you see the time t is equal to 0 solution. In the middle you see an intermediate time solution, and in the right you see a late time solution. So the initial solution shows you out here the solid volume fraction in the top panel and the velocity in the and the x velocity in the bottom panel. So the x velocity actually shows that we have a vortex out here which is interacting with this shock which is stationary on the mesh right now. So I'll go ahead and remove my markings. But please keep in mind that the top panels show the solid volume fraction and the bottom panels show the x velocity at different times. At time t is equal to 0 for the left panels, time t is equal to 0.23 for the middle panel, and time t is equal to 0.85. The intermediate time of t is equal to 0.23 was chosen so that it is the time when the vortex is halfway through the shock front, and you can see the vortex structure being stretched and distorted by the shock front. The late time at t is equal to 0.84 shows the solid volume fraction significantly distorted by its interaction with the shock front, but you can see that since vorticity corresponds to angular momentum and angular momentum is conserved, the vorticity is still preserved as the vortex has passed through the shock, and the shock has kind of stabilized out here and the vortex has cleared the shock. So with that we get some good insights that things are working according to the physics of the problem. Now we've been able to actually go ahead and do a shock bubble interaction problem. Of course it's not a real bubble. What has been done is that in this location out here we set up a modification in the bathymetry, and we went ahead and set up an initial shock front that was moving to the right, and as it moved it set up this very beautiful picture so that by the late time, which is shown out here, the shock is out here, but it has interacted with this variation in the bathymetry to produce this interesting bubble type picture out here. So this is for two-layer shallow water equations, and we have another shock vortex interaction problem, again at early times, at intermediate times when the shock is interacting with the vortex, and at late times when the vortex has flowed right through the shock and is on the other side of the shock. And again we're showing the height of the upper fluid at these three different times: the initial time, the intermediate time when the vortex is interacting strongly with the shock, and at the late time when the vortex has cleared the shock. And you can actually see that the upper panels will show you the height of the upper fluid at those three times, and the lower panels will show you the x velocity of the fluid at those 3 times. And this is actually showing you that things are working well even in that situation. We can also, for multi-phase debris flow, follow the same trick of setting up a non-constant bathymetry, and in doing so set up a shock bubble interaction problem. And here you see at a late time that the shock has actually traversed the bubble region, but the bubble has actually produced this interesting flow structures around it because of the interaction. And that is one interesting test problem. Many of the multi-dimensional test problems presented here are genuinely novel. And then we've gone ahead and for debris flow, for multi-phase, component debris flow model, we've gone ahead and done a shock vortex interaction. So the top 3 panels show you the solid height at different times 0.06 and 0.24, and the bottom panels show you the x velocity of the flow. And you can actually see that initially at this time, at time t is equal to 0, the vortex is set up and it's ready to kind of go into interaction with the shock. And you can see that even in the velocity field that the shock hasn't yet touched the vortex. Once the vortex begins to halfway flow through the shock at this intermediate times out here, you can see the solid height as well as the velocity field in that situation. And this right column out here shows you the solid height at a very late time after the vortex has traversed the shock, and the x velocity at that late time. Again, vorticity is a constant of motion. I'm sorry, angular momentum is a constant of motion. That is why you see that the vorticity in the vortex is very well preserved, even as the shock tries to disrupt the structure of the vortex. So it shows you that you're able to do a raft of multidimensional test problems, which is good. We've also done problems involving stiff source terms. So the thing I would remind you of is that finite difference we know is especially well suited for problems involving stiff source terms, because you actually do per zone and per time step, you only do one implicit solve here, another implicit solve here, so that's your second implicit solve here, third implicit solve here, and your fourth implicit solve here. So you do only 4 implicit pointwise solves per time step and per zone. And per time step, which is very good compared to finite volume schemes where you would actually have to do your implicit time stepping for the source terms at all different locations of the numerical method. So finite difference WENO schemes have a gigantic advantage over finite volume WENO schemes or finite volume schemes of any other sort when it comes to handling source terms, stiff source terms especially. And this is showing you a two-dimensional Riemann problem involving bare Nunziato flow, but the source terms have been cranked up so that they're extremely strong. And what the source terms do is that they manage to make this flow behave effectively like it is literally an Euler-like flow. And so with that, you can actually see that you set up a two-dimensional Riemann problem, which looks very much like a two-dimensional Riemann problem for Euler flow, except that it's being done with the bare Nunziato equations with very strong stiff source terms. So it shows that the method is capable of handling stiff source term problems. And that brings us to our conclusions. So our conclusions are that we have a new formulation of finite difference we know, where you can actually get by with one reconstruction per zone per stage, which is very different from using 2 reconstructions per zone per stage in the more classical finite difference we knows that we've had before. We see that the method is perfectly proficient at handling hyperbolic PDEs which are in conservation form, but it has a further giant advantage that it can also handle hyperbolic PDEs which have non-conservative products, so that is a good thing. The method can hold stationary discontinuities, and that is especially true because of the inclusion of the antidiffusive terms, and this advantage is useful, extremely useful for well balancing, which we have seen. The HLLI Riemann solver is a very nice touch out here because first of all it has a nice supersonic limit, and it also iterates to convergence very fast when non-conservative products are present. It also affords a very nice antidiffusive flux term, which is very easy to evaluate for any general PDE system. That is not true for an HLLC or an HLLD type Riemann solver, so there's a genuine advantage being posted out here. Treatment of stiff source terms is also very facilitated very nicely by this very nice scheme by Pareschi and Russo, and it basically dramatically reduces the number of implicit pointwise solves per zone and per time step, which is superb compared to what you would have in a finite volume scheme. We also have done many stringent test problems, including test problems involving well balancing and the preservation of contact discontinuities, and things work out well out there. Many of the multidimensional test problems that we presented out here are genuinely novel, and this scheme is significantly faster and more versatile than the finite difference we know scheme that we've had before. And the nice thing is that all implementation related details are given to you in a self-contained fashion in just one paper, so hopefully we can induce you to try it out. And with that, I will thank you very much for your attention, and hope to kind of talk to you at some other time. Thank you very much, and thanks a lot. Bye-bye.